Hello dear students, welcome to Pen and Paper Chemistry on YouTube, where we cover lessons related to organic, inorganic, physical and analytical chemistry. And the only thing the channel expects of you is when you sit down for these lessons, you have your pen and paper in your hand and of course a request to share these lessons with your friends and classmates so that they can also enjoy the benefit of learning chemistry in an easy way. So let's get started. We had already started with the preparation of aldehydes and ketones in the previous videos, and all the while it took me some time to prepare these very helpful flowcharts. So are you looking for a flowchart for properties as well? So there you go. We have only one part of this flowchart of properties of aldehydes and ketones, wherein we shall be talking about nucleophilic addition and nucleophilic addition followed by elimination. So let's get started with the properties of aldehydes and ketones. Addition reactions of aldehydes and ketones. Now we very well know that addition reactions take place across double or triple bond where there is unsaturation. That means our atoms are hungry to make more friends. Now why does addition reaction take place in the case of C double bond O? Look at the structure. Oxygen over here is more electronegative compared to carbon. So what does it do? It pulls the electrons of the shared pair towards itself, acquiring a negative charge, whereas the carbon acquires a positive charge. It is short of electrons now. Look at the reagent now, XY. It's a combination of an electrophile and a nucleophile. There are many examples that we are going to take up during the course of our lesson. So what will happen over here? If you see, the positive goes to the negative, so the electrons of oxygen tell X positive, oh look, I have electrons, I can help you out. Whereas the Y negative offers its electrons to the carbon. With the result, what do we have? We will have addition across the double bond forming OX and Y. Now what type of an addition reaction is this? Is it electrophilic, nucleophilic or free radical? Although we have covered this topic under the reaction mechanisms playlist, it is difficult to predict just by looking at the reaction whether it is electrophilic, nucleophilic or free radical. So what do we need to do? We need to look at the mechanism of this reaction. When we look at the mechanism involving the addition of a neutral molecule, so how have I depicted that neutral molecule made up of two parts, an electrophilic and a nucleophilic center? That's how I have tried to make it easy. Now when it adds across a C double bond O, that means that C double bond O is either in the aldehyde or the ketone. Now we know the property of C double bond O. Oxygen is more powerful. It is able to pull these electrons of the shared pair towards itself. Now when it does that, it acquires a negative charge. With the result, my carbon will be left with a positive charge. Now oxygen is happy to keep the electrons to itself for now. So carbon is hungry. It is hungry for electrons. So what does it do? It goes, or not exactly goes, it attracts the nucleophile towards itself. Actually, the arrow should be the other way around. In other words, the nucleophile comes and tells carbon, I can give you my electrons. I am happy to share because I am anyway looking for a positive species. Now, why does it do that? Depends on the condition of the reaction. Whereas our O negative is left with its electron pair because it's not wanting to share, right? So it's left alone. You should always share, just like you will share the knowledge from this video with your friends and classmates, right? Now look at the structure of carbon over here. It was forming 3 bonds, and one of it is a double bond. That's a pi bond. In other words, our carbon over here is sp2 hybridized and our structure is planar. But in the second case, that means once this intermediate is formed after the attack of nucleophile on the carbon which is positively charged, you see over here, now there are 4 bonds being formed and all of them are single bonds. By the way, you must be wondering what are these dashes and this wedge. This is nothing but representing a molecule in 3 dimensions. So the dashes that you see means the bond is inside the screen, whereas the solid line that you see over here, the wedge here, this is outside the screen, whereas these two are on the same plane as your screen. So this is a 3-dimensional structure. For greater detail on hybridization and the structure, please visit the playlist on hybridization separately on the channel. So that means I have an sp3 hybridized carbon over here and our structure is tetrahedral, right? I hope you are drawing along with me, or you would have paused the screen in order to draw these structures first. Now look at what happens here. Now oxygen sees, oh my, look at this, carbon is so happy being stabilized by the nucleophile, whereas I am carrying the burden of these electrons alone. What do I need to do? Okay, it offers its electrons to the E positive part. That means the positive part of the reagent. So what do we have over here? We had the nucleophile already attached, and the electrophile comes and attaches itself to O negative. With the result, we have our final addition product. Now, if you are getting confused with E positive and Nu negative, to simplify things, you can also write it as H positive and X negative. So, the H positive will go to the oxygen and X negative will go to carbon. Now, this by no means HCl, HBr, HI. No, X can be any negative part. That means it can be any nucleophile over here. What nucleophiles are there, we shall see further on in the video. Another thing to be noticed over here, the first step of our reaction. Oh, this is not step 2, this is step 1. Sorry. So, the first step of our reaction is a slow step, because see, they have been long time friends. Why would they want to separate and go out of the way? So that is why it's a little slow step. It's quite stable. On the other hand, now that oxygen sees that carbon is having all the fun by sharing its electrons, it quickly wants to turn itself into an addition product. Right? So the second step becomes fast. Carbon over here is carrying a positive charge. In other words, the carbon here is electrophilic. C positive becomes electron loving. Electrophilic. Philic is loving and electron. So it becomes electron loving. On the other hand, The O negative is carrying a negative charge. That means it has an affinity for positive center. That means it is nucleophilic, nucleus loving. And what charge does the nucleus have? It has a positive charge. That means it's positive loving. We had started with the question, what type of addition reaction is this? Electrophilic, nucleophilic or free radical? And I said that we look at the mechanism in order to determine this. So what we observe in this reaction is that the first attack is taking place by a nucleophile. That is why this reaction is termed as a nucleophilic addition reaction. So addition across double bond involves nucleophile as the first attack, although both are getting added, nucleophile as well as electrophile. But because the first attack or first attachment takes place by the nucleophile, that is why we call it as nucleophilic addition reaction. If you have written this mechanism, I will share the step 1 and the step 2 details with you. You can note it down over here, so that in case you want to revise later on, you can do it by looking at these steps. So the first step is attack of nucleophile on polar C double bond O. C is the electrophile, O is more electronegative, so it's the nucleophile. sp2 hybridized carbon changes to sp3 hybridized carbon. Planar changes to tetrahedral. Yes, you notice over here, I am not putting the dashes and the wedge over here. I have tried to simplify things for easy understanding. Step 2 is addition of E positive on the oxygen to form neutral molecule, and we have already depicted it in the mechanism above. I will also be sharing these notes and these screenshots on the site Pen and Paper Google site. It's not a normal www site. It's a Google site. I don't know what technical term we call it as, but if you Google pen and paper, chemistry. Yes, just the name, just like the name of the channel. If you Google pen and paper chemistry, earlier it was called learning chemistry is fun. Now we've changed to pen and paper chemistry. Right? Written? Have you written? Okay, let's go ahead then. Aldehydes and ketones, both are carbonyl compounds. So what is their order of reactivity with respect to nucleophilic addition reactions? Again, coming back to making things simple. So when you have to write the reaction, you can just put it as negative, positive, positive, negative. Yes, I'm going to put the partial sign so that it's easier to connect. So positive will go to negative and the negative will go to positive. And what do we have over here? COH and then X. As simple as that. This is how you're going to write the addition reactions. Now, you have various options. HC double bond OH, CH3, C double bond OH, CH3. I'm going to take 3 examples to make things easier to understand. First of all, look at the 3 structures. Which of the 3 carbons? So we know that the carbon here becomes electrophilic, right? So which of the 3 carbons here would be most easily approachable? Which is least crowded? Look at the structures or look at the attachments to each one of them. Now this has got only 2 small hydrogen atoms. This has got a little bulkier now. You see, it's become a little heavier because there's an alkyl group attached to the carbon. Oh my God, look at this. This has got even heavier than that, right? So which of the 3 carbons is most easily approachable? Yes, the first one. That means methanol would be the happiest to undergo nucleophilic addition reactions, right? Followed by our ethanol. Yes, because ethanol now has an alkyl group attached to it. And the last to come in the series would be the ketone proper known. Why? Because of what we call as steric hindrance. Now supposing I have to compare two aldehydes, so I have C2H5, C double bond O and H, and let me say I've got this. Now both of them have an alkyl group. Now out of the two of them, which is more easily approachable? Yes, the first one is more easily approachable. So look at the steric factors. The second fact to look for is the electron donating characteristics of the group which are attached to it, whether they are electron donating or electron withdrawing as well. So here I've got hydrogen. Of course, the electronegativity is equal. Now look at the alkyl group. You remember we did the inductive effect, electromeric effect, mesomeric effect and so on. So what kind of effect is shown by an alkyl group when attached to another carbon? Is it electron withdrawing or is it electron donating? Yeah. So in short, you will find me using, or you will find in a lot of textbooks as well, EWG. That means electron withdrawing group, or EDG, that is electron donating group. That means it is giving, right? Now we know that our carbon here gets positive, right? And oxygen, because it withdraws the electrons, becomes negative. If the desire of this carbon is satisfied in-house itself, that means if I have an alkyl group, so I'll talk about the alkyl group here. Now this has got an alkyl group which is EDG, electron donating group, right? Now because it is electron donating, this hunger of carbon for electrons is partially satisfied. So do you think it will be readily keen to get attached to this nucleophile as compared to a carbon over here which has got a high positive charge because there is nobody to give electrons to it? So do you think out of the two carbon atoms, which one would be more keen to attach itself to the nucleophile or to attract the nucleophile towards itself? Yes, of course, the one which has got high concentration of positive charge, right? Now which one is it? Think about it. This is donating electrons, so it's reducing the positive charge on the carbon. So what do we have again? So we will see over here that our ethanol will be less reactive compared to methanol. Now let's talk about ketones now. Ketone has got two alkyl groups which are both of them electron donating. Now because these are electron donating, what will happen? The ability of this carbon to attract a nucleophile towards itself will further decrease, right? So that means the reactivity of a ketone because of this behavior will be further lower than that of a substituted aldehyde. Yes. So in both the cases we found that methanol is the most reactive, followed by ethanol and followed by propan-2-one, right? So that means we can say that aldehydes in general are more reactive than ketones, and in that also methanol. In the case of aldehydes, methanol will be more reactive than other aldehydes. Now what about if there are electron withdrawing groups? Look at the two structures that I have drawn over here, ethanol and chloroethanol. Now this chlorine is highly electronegative, remember, so it has a tendency to pull the electrons towards itself, although it is attached through the carbon, because it is, it's going to be a tug of war. Chlorine is going to pull from the carbon, carbon is going to pull the electrons from the carbonyl carbon over here. With the result, the positivity of this carbon is going to increase. So now tell me, out of the two of them, which one will be more reactive, 1 or 2 towards nucleophilic addition reactions? Don't forget that we are taking case specific nucleophilic addition reactions in carbonyl compounds. Yes, of course, the second one will now become more reactive than ethanol. Chloroethanol will be more reactive than ethanol. Right? Have you noted this down? So in case you want to note down the points in short for further revision, you can note over here, lower steric hindrance, more the reactivity, therefore aldehydes are more reactive than ketones. Electron donating groups will repel the nucleophile, thereby reducing reactivity. So what did we do? We put the order of reactivity as 1, 2 and 3. On the other hand, electron withdrawing groups, just now we saw the case, will increase the reactivity. So how did we put the direction? This is more reactive. It's easy to take screenshots, but I would prefer that you write these down yourself, because your two revisions are taking place simultaneously. You are watching this video, you are listening, and then you are writing. So all your sensory organs are involved in this lesson, and trust me, you will be very happy by the end of this short video. Although we will not be able to cover all the nucleophilic addition in this video itself, I shall carry it forward to the next one. But you don't forget your pen and paper when in the next video we start writing down the reactions for nucleophilic addition. So stay connected with your pen and paper in hand.